Hello everyone, thank you all for joining us today and for being part of Data Science, Machine Learning and AI group. My name is Bojana and I manage event marketing at Syntelli Solutions, which is data science consulting firm based out of Charlotte. We offer a wide variety of services including data analysis, master data management, business intelligence and reporting, machine learning, and AI across industries like healthcare, manufacturing, financial services, and insurance. We host this monthly data science meetup, usually in person, but for the time being online. And while Charlotte is the biggest meetup, we also have chapters in Birmingham, Alabama, and Jacksonville, Florida. For those who don't know, this is our second online meetup with joint forces with our two other chapters. So continue to follow us on Syntelli's social media platforms as we are to announce more events to come. We already have one event lined up. It's a virtual panel with 5 healthcare experts from the southeastern region. You can find more details on the syntelli.com. And finally, moving on to our speaker for today, we have Nathan Danneman. He is a chief data scientist at cloud and data science company called Data Machines. He will walk us through the feed-forward and convolutional neural networks. A quick intro on Nathan's background. Nathan is an applied statistician who thinks the world is best understood through strong theory vetted by rigorous empirical testing. While his doctoral work focused on social science phenomena, he has since worked at the intersection of social and networking sciences and statistics, often working against a very large scale of data sets. He thinks of himself as a dynamic generalist, both in terms of the methods he is familiar with and the domains in which he has applied them. Over the last few years, he has applied item response theory to big text data, estimated spatio-temporal models of multi-measurement patterns, and cross-categorized enterprise-scale network traffic with latent variable models. Underlying all of this above is a passion for extracting insights from large, complex, and difficult data. So before I hand it over to Nathan, I would like you to ask you to submit your questions in the Q&A sections below. We are going to address them at the end. Nathan, you can go ahead.
Dropout, wherein you probabilistically set certain parameters to 0 during the training process to avoid overfitting. And then also regularization, which works just as it does in, for instance, lasso or other flat models, where you constrain basically either the sum or the norm of parameters. Okay, I encourage any of you who are interested to head to this playground.tensorflow.org to see how these hyperparameters affect the actual outcomes of real models over toy data. All right, and just as a further hint, we typically start with an overly expressive model. If an overly expressive model, so that's one with lots of neurons and lots of layers, can't fit your training data, then there's either something fundamentally wrong or there's nothing to learn there. We typically like to track measures of interest on test data and terminate when that plateaus. Again, that's premature halting. And then lastly, just as a tip to sort of get people started rapidly, you usually want to match the problem type, the output layer, and the loss function. And so here's a quick little cheater table. I'll just read across the first row there. If your problem type is regression, that is, you're predicting something that is continuous and unbounded, the output layer should be a 1-unit linear layer, probably, and the loss function should be mean squared error or something akin to that. Okay, so when might you use a feed-forward neural network for regression or classification? And in truth, the answer in most applied settings is probably never. They're slower to estimate and don't give you a lot of benefits beyond, for instance, gradient boosted trees, which are much faster to fit and require no specialized software. Typically, if you're using a deep neural network for something, you have a problem that's a good bit harder than a plain vanilla feed-forward neural net would solve. And it's usually it gets classed as a perceptual problem. And that's kind of my entree into image analysis. Okay. So one place where people do get value out of neural nets is with image classification and other image-related tasks. You might be thinking to yourself, okay, images, they're arrays, right? Height by width by 3, RGB typically. You could just unwrap that into one long vector and then use a set of fully connected layers or a feed-forward neural network to try and do classification. It turns out a model like that would have tons and tons of parameters, and the pixel location is relative in a sense that your vector inputs are not. Right? So if you have lone data, what's in that first column is always what's in that first column. Whereas if you have an image, you can have lots of different images of, say, trees, but the tree could be at different places in the image. That's what I mean by pixel location is relative. So convnets are an effort to sort of solve those things. And they solve the first problem by parameter sharing, which I'll talk about in brief in a moment. And then they solve the relative pixel location problem by looking at an image hierarchically. Okay, I'm going to take a stab at explaining convolutional neural networks. They're a really obnoxious concept to try and get across succinctly. And so I'm going to kind of come at it twice from slightly different perspectives. If it only halfway clicks for you, that's okay. I've got some pointers at the end that you can go take a little more a more in-depth look and do some more reading to try and track it. Okay, here's the big idea. We're going to find a set of micro pictures that roughly capture the content across patches of all of your different images. That's sort of the convolution step. And typically that's followed by a pooling step, wherein we let a single pixel represent its whole neighborhood. We sort of drop the rest of the information from that neighborhood, or just summarize it with one pixel level of information. If you repeat this process, you end up with a hierarchical view of an image. So let me just describe each of these ideas in a little more depth so you can think about it more concretely. All right, so the first bullet was find a set of micro pictures that roughly capture the content across all patches of all images. So you don't actually locate these things, you estimate them from your images. And this is what they might look like. It's a whole bunch of, in this case, I think it's 10 by 10 pixel size patches that through some combination of them, you can more or less recreate all the variants across. And then we have to learn the weights and biases for these hidden and output layers. All right, that sounds like a lot. Here's a code snippet to demonstrate that it's actually quite easy. So we import some different layer classes from Keras. And let's see if I can annotate this. Great. So here we instantiate our model, just like before. On this line, we're adding a convolutional layer called com2d with 32 filters. And the filter size or kernel size is 5 by 5. The input shape to that is just whatever our input shape is for our images. For instance, 256 by 256 by 3. We'll then add a max pooling layer of size 2 by 2. And that means that a 2 by 2 patch coming out of the preceding layer gets represented as a 1 by 1 patch coming out of this layer. We then flatten that, so that is turn that height by width by depth representation into a single vector. We add a hidden layer, and we add an output layer with the number of classes that is as deep as the number of classes we have, and we are done. So this is an instantiation of a simple convolutional neural net with Keras. See if I can make that annotation go away. Great. And here's how you would then compile that model and then fit that model. Okay, let's talk about a couple of kind of pragmatic issues you bump into. The first question to ask yourself if you think you want to run a convnet is, are your images special? That is, do they have very low level or higher level features that are fundamentally different from other broad image data sets available kind of out in the wild? The answer is probably no. There are large models that are trained on sort of everyday image data that you can pull down and use or chop the last layer to off of and fine tune to your purposes. That's probably the right way to go, especially if your images aren't special or you don't have a lot of them. So if you don't have enough information to learn all of these hierarchical filters with a lot of fidelity, you can just get some general purpose ones that are already trained. Are your images all the same size? If yes, you're in a very convenient world, and kudos to you. If not, you'll need to think hard about resizing all your images so they're the same, because ConvNets expect basically same size inputs coming in, or you'll need to use a special layer to account for that, some sort of parameter layer. And then another question as you sort of get started on a ConvNet related project is, are your images large? Do you have a lot of them? If your answer to either or both of these is yes, you almost certainly are going to want to use a GPU to increase your processing speed. Otherwise, you will be waiting a long time for your model to converge. Okay. I'd now like to just pivot and mention sort of a hard use case that I got to wrestle with recently, my team got to tackle. So we're a part of a big research program called Media Forensics. And the challenge of that program is to write software that identifies altered images. So this is sort of attempting to programmatically answer the question, was this image photoshopped? And so researchers, other than my team, write analytics that output two things for every image at runtime. A score, so it's a probabilistic assessment of whether or not an image was manipulated, and a mask. And that's a 2D representation that's the same size as an image, that is where the pixel intensities represent the probability that that particular pixel was altered. My team's task as part of this challenge is to try and fuse the masks, one for every upstream analytic, of which there are, between 30 and 70, depending on how you count, try and fuse those masks into a single optimal mask. And so team 1 says the manipulation is in the upper left, team 2 says it's in the upper right, team 3 says it's all over the place, team 4 says there's no manipulation here that I can see, and our task is to take all the information and synthesize it into a single predictive mask. All right, so here's a little bit of example data. So a probe image might look like this picture on the left, right? It's like a parrot standing on some rocks against a gray, cloudy sky, and a mask returned to us from a team upstream of us might look like that thing on the right. And that's them saying, I'm not really sure what's going on here. Maybe the parrot is photoshopped or was added or cropped or something. Maybe the rock doesn't look right to me. I'm not super sure. Notice that it's not binary, it's grayscale, and it's very chunky. All right, here's an example mask from another team who, similarly, if I had to put words to this, I would say that this team thinks the sky to the right of the parrot is definitely manipulated in some way. The parrot itself maybe, but maybe not anything else. But you can see there are kind of these odd artifacts elsewhere. And here's another example mask. These people think that the sky above and to the left of the parrot looks wrong in some way, and then the sky to the right of the parrot is wrong. They seem ambivalent about the parrot itself, and they think the rocks look maybe okay. A lot of really heterogeneous signal here. Okay, so here's a little bit of kind of intuition about what I wanted a model in the model class to deal with. Right? First, we need some spatial smoothing. If you look back at that example data, you'll see that what was done to an image probably is done in a tight spatial area with clear boundaries, but those spatial masks were very fuzzy, so we're going to need to smooth across them. We're also going to need to handle missing data. I guess a caveat I had not already mentioned is that some teams put out no masks some of the time when they're not sure. We also want a really lightly parameterized model. That is, we can't have an extremely deep model with lots and lots and lots of neurons because there's not a ton of training data available to us. And then, of course, we're going to want the output of our model to be the same shape as the input image, even though the input images could be many, many different sizes and shapes. So these are some of the sort of complicating factors. All right, so the approach we took, and apologize because I can't share sort of the details of the model or the details of the results, but I can kind of talk about them notionally. The general approach we took is to use large filters to get spatial smoothing. So the intuition there is that whether or not a particular pixel was manipulated or not is probably a function of a pretty large area of pixels around it. That helps us deal with some of the fuzziness of the upstream researchers' kind of cruddy output masks. We didn't use too deep a model, and that helps to squeeze down the number of parameters. We pre-size all the images to 128 by 128, and at the end of our pipeline, we resize back to the original image shape. And we added a default image mask of all -1s as sort of a placeholder to handle missing data. And then the actual class of model that we used is a convolutional neural net, very similar to the one we just talked about. Later, we actually added information from an image segmentation model run over the same images to try and capture the intuition that if someone alters an image, they probably altered a thing in the image and not sort of a random area. Okay, so here's an example autoencoder setup. And so an autoencoder is a model that kind of squeezes the representation of image down really small and then expands it back out a little bit at the end. And the hope is that by doing that bottlenecking, you can sort of forget some of the idiosyncrasies of your training data and learn more general patterns. So again, we start by calling mod as a sequential model, and then we add a convolutional and a pooling layer. I'm not going to sort of speak to the batch normalization process right now for lack of time. And then we upsample back up to the larger image and then have a one level, let's see if I can point to that. A one layer convolution at the very end because our output needs to be a binary representation. All right. And so I sort of didn't get permission to give you a sense of exactly how good we are at this. What I can say is our goal was to do better than the best single analytic, and we were able to do substantially better than that. And so we were able to prove the value of fusing all of these different performers' masks together into one sort of joint mask that ends up being operationally more useful than any of the sort of underlying data by itself. All right, I've come to the end here. I wanted to leave you some breadcrumbs if you want to poke around further. Here's a smorgasbord of resources that I've sort of vetted and I give to my team when I want to warm them up to ConvNets. I find it very tedious on the internet these days to get good information because the field is moving fast and the internet lets anyone write anything about anything. So here's some sort of lightly vetted resources that go from sort of bloggy level all the way up through paper level. Again, if you want to understand hyperparameter tuning for deep neural networks, I really recommend this playground.tensorflow.org. It's a really nice way to build your intuition on what's happening with those hyperparameters. Okay, and with that, I'm going to open it up to questions. I think I'm going to have to ask our hosts if there are questions because I can no longer see that chat box. But if you want, I'll just mention now, feel free to reach out to me. There's my professional email. That's a pointer to my GitHub where you can get these slides, and then there's going to be a large set of code associated with them that's fairly self-contained. So feel free to pop over there. Later this evening, I'm going to make that public once I've tidied it up a little bit further.
There are two questions. If you want me, I can read it to you now.
Okay, I can't seem to access. I see that there are some, but I can't seem to access them.
Yeah, no problem. What is the binary difference between binary cross-entropy and categorical cross-entropy? That's a question from Terence.
Hi, Terence. Great question. At the sort of intuitive what to do level, the difference is you use binary cross-entropy if you have a binary classification problem, right? Like the classic lone default kind of example, like predicting whether something is a yes or no answer or 0-1. And categorical cross-entropy is more suited for if your output can have K is greater than 2 possible classes. So if you're trying to predict whether, let's say, an image is a bird or a cat or a dog, then you want to use the categorical cross-entropy loss function. Mathematically, one is a pretty straightforward generalization of the other. Great question.
Okay, do you want me to continue with the others? Because there are 3 more now, or you want to address them at the end?
We're at the end, so I'm happy for you to kind of take them in whatever order seems reasonable to you.
Awesome. So Robert has his next question. So Keras is now included in TensorFlow 2.1.
If that's a statement, awesome. And if that's a question, I'm not sure. It might have been a question about which versions of TensorFlow Keras supports. Up until fairly recently, they were kind of just behind, which for most of the stuff I've been doing hasn't been a deal breaker to me yet.
Okay, hope that answered Robert's question. Then we have, in your experience, are there cases where CNNs aren't as accurate at the XG boost with non-vision use cases? That's a question from Clarice.
In my experience, are there cases where CNNs are not as good as XGBoost for non-vision use cases? Okay, so yeah, I made a pretty strong claim in sort of the first third of the talk about how I don't really use feed-forward neural networks for straightforward prediction problems. And that is true because models like XGBoost I find fast and accurate. So for non-vision problems, I'm not sure. There are cases where you want to use a convnet, so where you want to sort of have features or the output of features be a function of surrounding features. But most typically, if you're using a convnet, you're talking about image processing work or other work where you need smoothing across some dimension that you can specify beforehand, kind of mechanically. So not like a full-on kernel, but more like a sliding window style function, which is functionally what a convnet is. If you're really in a world where you have a perceptual problem, so I've seen convnets almost exclusively used for image or video. I think I've seen them used in audio, where you can imagine a convolution through the spatial axis. If you need that kind of perceptual ability, a deep neural net with convolution is the way to go. If you don't need that, then models like XGBoost tend to be really performant. I hope that was an answer.
Hopefully. Thank you. And we have one more. Actually, Terence is adding something on your previous answer. But I saw you use binary cross-entropy for the iris dataset, which has 3 classes.
Oh, then that's a mistake on my part. Thank you, Terence. I'll correct that when I repush.
Awesome. That means that he was following.
Yeah.
Shweta.
This is me actually writing a note to fix that before I make this public. Thank you.
Awesome. Then we have a question from Shweta. Can we please talk about the applications and nuances of using Auto-Encoders over convnets, please?
Oh, yeah. So that term kind of slipped into the talk right at the end without a lot of discussion. So let's see. Let me try and define those 2 terms and then talk a little bit about their use cases, because they're sort of they may or may not be, they can be related. And let me see if I can move my screen so that I can face the camera a little more gracefully. Oh, hey, there are the questions. Neat. They were hiding behind my presentation. All right. Cool. So a convolutional neural net just means that you're using this convolution operation, right? So that means you're taking information from surrounding pixels and you're using a filter to try and capture groups of pixels, and then you're probably consolidating that information with a pooling operation. In an autoencoder model, that's a description of the high-level structure of the model, whereas ConvNet is a description of what happens in a particular layer or pair of layers. An autoencoding model starts usually with an input that is large, either a large vector or a large spatial extent, like an image, and it squeezes it down to some kind of much smaller representation in the middling area, and then expands it back out towards the end. The reason to use an autoencoder, there's several. So for a while, it was sort of in vogue to have an autoencoder and have a model try and predict X with X, which sounds really weird. Like, if I have my input, why do I try and predict my input? And then the point was that you would then lift that intermediate representation, that small representation, and do other things with it. So you'd use that as a hash or a representation in like R2 or R4 or for plotting purposes. Also, autoencoders for denoising purposes were kind of in vogue for a while, where you would put an intentionally noisy version of X in one end, and you'd have the clean version of X as the target, and you could kind of learn a model for denoising, for instance, images or even tabular data. My sense of the potency of that, especially for tabular data, was kind of middling as compared to like other imputation and error correction techniques. All right, that might have been a bit in the weeds, but and so those things can clearly be crossed together like I did, right? So the model I described at the end was convolutional because it used the convolution operation, but it was also auto-encoding because it started with a thing that was length by width by number of upstream analytics deep, and it squeezed all that down into a smaller space to try and forget the idiosyncrasies of each one of my training data examples, and then flattened it because I wanted an output in 1D, but then expanded it back out to be the size of the full input image.
Do you want me to read it out?
Actually, I can see it now. Let's see. I think I see two open questions. What is best for stock data and prediction? So I think XKCD, as in many parts of life, that's a webcomic, has the answer to this, which is if you're an engineer, you probably think you're good with numbers and systems, and you might think, hey, there's the stock market. That's just numbers and systems. Maybe I'll write a predictive model against that. And I urge you to have fun with that and not put your own money into it. Maybe put someone else's money in. I guess less flippantly, for stock prediction, it sort of depends on what you want to do. If you're talking about univariate stock prediction, as in I have the history of this one stock's prices maybe at the hourly or daily level, and I want to know what it's going to be for the next day or the next hour, people usually use sequence-based models like LSTMs for that. Again, my hunch is they're not all that, probably is not going to be all that predictive. If you want to use the current value of a stock and other stocks, so perhaps in either competing or peer sort of sectors, you could then take, again, sort of an LSTM-based approach. The LSTM stands for long short-term memory. It's a model for sequential data. I have a hunch that that's what was being done 5 years ago, and now something more sophisticated might be being done if you're to go to like a brokerage house. That's pretty far out of my area, so that's kind of a wag. Let's see. Shweta asks, I've used autoencoders for anomaly detection. That's a great use case, but not in case of images yet, as we use filters in ConvNets. Can you give an example of a type of filter to denoise, say, images? I sort of alluded to this a minute ago. I've seen examples of denoising autoencoders where you take an original image and you intentionally add some noise to it, like perhaps a little bit of blur. In fact, I imagine this is how the image sharpening revolution has happened. They probably learned models where they take an original image that has and they add a tiny bit of blur to it, and they try and predict the original image, and in hopes of learning a model that can denoise images. So you don't have to use special filters. The magic is in sort of the architecture, the structure. How much squeezing do you do? How fast do you ramp back out to the original image size? Let's see, maybe that was the answer. And then, oh, just a follow-up question. Yep, thanks.
Hope that answered everyone's question. Guys, do we have any more questions that we want to submit? Nathan, do you want to add something else?
Oh, just a big thank you to everyone. It was a little tough to give a chat to a virtual room full of people whose faces I couldn't see. So I don't know if people were nodding along or nodding off or squinting in confusion, but hopefully that was useful. And like I said at the end there, feel free to reach out to me if you have follow-on questions. I'm going to try and get all this up on GitHub later. Yeah, and thank you all for your attention and the invitation.
Thank you all for your presentation and being speaker today. We will be sharing this recording on our YouTube channel. Follow us and you will get it. Once again, thank you all for joining, and have a good rest of the day.
Thanks, everyone.
Bye-bye.
Cheers.